Hello and welcome to Electrostatic Discharge and Turbine Lube Oil System. This is a webinar and my name is Daniel Alessandri. I work for Call Corporation. It's really my pleasure to welcome all of you here today. For the next 35 minutes or so, we'll be discussing the issue of static charge, static discharge, and how it can affect lube system in general, but in particular here we'll be interested in knowing how they can affect turbine lube oil systems in particular. So briefly, this is what we'll be discussing today. Obviously, we'll start by discussing why this phenomenon happens. We'll talk about oil behavior and really the basic concept of what makes a static charge happen and then dissipation and discharge. We'll see where it tends to happen and why and how it does happen. We'll also talk about why it's really a problem that may not go away. It's actually a growing concern, and it has to do with engineering consideration and some chemistry consideration that we'll touch on a little bit. We'll talk about the typical symptoms and consequences of a major ESD problem in a system. We'll talk about degradation of fluids and components, what happens. We'll spend a little time discussing specifically the filter issue. And we'll give a few tips and direction when it comes to preventive measures. So again, we'll talk about how filter consideration can play a part and also be part of the solution. And then we'll touch briefly towards the end on other subjects that we won't be able to cover fully today, but things like the influence of air, the influence of moisture, and things like micro-dieseling and so forth. We'll discuss a little bit of varnishing issues. And finally, we'll conclude and have a quick Q&A question. So to that extent, feel free to use the Q&A box on the left of your window. That's how you can ask questions anytime during the presentation. And at the end, I may not be able to answer all of them today live with us, but all the questions would be compiled along with their answers and then republished as an on-demand document along with the presentation that you're seeing today. So without further ado, oils can be conductive and more or less, and that has to do with the fact that in their true sense, so a true hydrocarbon, pure oil is actually an insulator, and the best example is the use of dielectric oils to insulate power transformers. The oil can be polar, which is really why it tends to stick to metallic surfaces, and it plays a part in how it lubricates. So the polarity of the oil is something that is used. More importantly, this insulating characteristics of the oil can go away very easily, and contamination will be responsible for this. So minute amounts of contaminants down to a few ppb in a system, these are responsible for a rise in conductivity of the oil. So in practice, really, all types of oils can conduct electricity to varying degrees depending on their chemical makeup, more importantly, depending on the contaminants that are present along with this hydrocarbon chains, if you will. Static charging has a lot to do with velocities or fluid dynamics. In its most basic form, a static charging is really the exchange of electrons between two materials. So oil against metal in our case, or oil against plastic when we start talking about filters. But in general, two things rubbing together, depending on how their polarity is present or not, will tend to charge in opposite direction from the other. And that's really the basic of static charging. So it is typically related to a few things, but a big contributor to charging is shear stresses, not just between an oil and a metal surface, but also between what I would call layers of oils together. And to understand how that can happen, you can look at the little diagram at the bottom where I see a very simplistic schematics of a typical pipe, a typical velocity profile of a fluid going through it, in this case oil, and what's important to remember here is the amount of charging is proportional in a way, or at least dependent on the velocity gradients. So the difference in velocity between two adjacent oil layers, if you will, is what's going to drive shear stresses and this rubbing effect that will create charging. As a result, you can expect this charging phenomenon to be more prevalent close to the side of the pipe itself. And you can see on the diagram, this area is where the speed basically goes from zero at the surface very quickly to the typical average velocity of the fluid. So there, velocity gradients are important, shear stresses are important, and you're going to create charges more importantly on that end. So static charges will tend to happen in tight passages, and that's related to what we just discussed about velocity. In a situation where oil has to go through small openings, for example, filters or servo valves or bearings, especially when they have very tight clearances like in roller bearings, there is a chance there where the velocity and the shear stresses will overwhelm the system and you'll start charging in that location. Charging increases with viscosity because it plays a part in how the shear stresses are created, and of course differing electron affinity between the two materials. So you have to have some polarity on the materials to charge them. So between oil and metal, oil and plastics, and between oil components themselves, as we've seen earlier. Interestingly, what you see on the top chart here is that for same flow rate, if you go through a large pipe versus a bunch of small ones, then the shear stresses are going to be tremendously different. In this example, on the left side, you see the equivalent of what, for example, a filter would be, which is a multitude of very small channels where the oil has to push through. So for a given flow rate, you will create a lot more charging, a lot more shear stresses in a situation where you multiply the number of small openings as opposed to having a one large pipe. So we discussed a little bit how things can charge up, right? How they can accumulate charging. But really, in practicality, charging is not necessarily the problem. Really, problems occur in the discharge phase or dissipation. So how the charge will dissipate over time is really what's going to drive whether you're going to end up with a critical situation or not. The time it takes for a certain charge to go back down to zero is called relaxation time. And that time is mostly dependent on the conductivity of the materials at play here. So in a high conductive, or what we call high K, K being a measure of conductivity, charges can dissipate as soon as they are created if the conductivity is high enough. And there you have no problem. So in this example that you see at the center of the slide, if you have a pipe wall with fluid going through it and actually going through a filter material that you see here represented in light beige, you'll tend to charge the fluid. And by charging the fluid, you'll charge the pipe around it, which is not a problem if the pipe itself is grounded. So you'll eliminate this charge on the piping readily if it is grounded. The filter media, however, also will pick up charge, and usually, especially in modern filtration, the filter material is not grounded and is actually quite resistant to current. So when the filter charges, it will maintain its charge for a while. The oil will pick up opposite charges, and then the oil will carry this charge all the way downstream, and that's what we call streaming current. If the fluid itself is non-conductive, then this charge is going to remain in the flow. If, on the other hand, the fluid is very conductive, then this charge tends to dissipate. And there is a dynamic relation between initial charge and a charge at a certain time t. And without going into too much of the mathematics, it's a exponential decay with time. So you start high, and then you're going to decay exponentially, and the exponential factor will be dependent on the value of conductivity, so K. If you track K in the couple of formulas you see on the left side, you'll understand that when K is large, then the charge tends to dissipate very quickly, and that's mathematically driven by this equation here. So interestingly enough, as I mentioned earlier, there are some engineering consideration and chemistry consideration that will affect how we charge up a system with static charge, but more importantly, how these charges can dissipate or not. So let's look at a couple of these engineering considerations that will affect shear stresses and, by extension, the charge buildup in the fluid. We tend to run at higher velocities on more modern systems. The oil volumes tend to be smaller to save on cost and space, and therefore velocities tend to increase with the result of increasing shear stresses in the system, especially when you go through tight passages. More frequent starts and stops when we talk about typical combustion turbines, for example, means that thermal variations are going to cycle at a higher frequency as well. So you tend to get those viscosity changes on the oil when it gets colder versus hotter, and that will play a part in increasing the amount of shear stresses and therefore the charging in the fluid. That combined with the drive to protect components down to smaller sizes, so when filters get finer, the passages get tighter, and that also increases the rate at which an oil will charge. So this need for better protection actually plays a part in the prevalence of this phenomenon. Materials decision play a part, whether you use metallic filters or plastic filters will play a part in how they interact with the charging phenomenon. So engineering consideration can play a part in the charging phase, but they can also play a part in how we can dissipate that charge. So having no ground on any of our components means that the charge will stay there until it finds its own path, which could be destructive through arcing. Increasing resistivity of the materials, the oil, but also the filter media, will also prevent dissipation. And the case of the oil itself is quite interesting, and we're going to spend a little time talking about Group 2 base oil, which is this new trend or this new formulation that are becoming more prevalent in turbine lube oil system and other type of lube and hydraulic fluid systems. So let's spend some time discussing a little bit what a Group 2 base oil really is. And fundamentally, it has to do with how the oil is made and refined. You can see on the left side 3 cases. One is a saturated hydrocarbon chain, and then unsaturated and polyunsaturated at the bottom. Typical Group 2 base oil tend to use much more saturated hydrocarbon than their Group 1 counterpart. That has to do with how the oil is made, and it is typically hydrotreated as opposed to solvent extracted the way the Group 1 used to be. That has a few major implications. One is, of course, the oil base stock becomes a lot more chemically stable. The fact that it is saturated means that it doesn't have a lot of space and energy to interact with other chemicals or contaminants that could be present. So resistance to oxidation, resistance to aging is a clear benefit of having saturated hydrocarbon in the base stock. It also helps the oil to be more resistant to pressure loads, which helps in its lubricating ability. And overall, the oil, the Group 2 base stock, is a lot purer. Much lower sulfur, lower metallics, lower paraffinic materials. So they are designed to last longer. They are more resistant to aging. They are more resistant to pressures. And they are purer. So that's all good. That's all good unless we forget that purity comes at a price. And typically this price is higher resistivity, lower conductivity of this oil. So now you can imagine that where previously a Group 1 could charge but then dissipate quite easily the charges because it was more conductive, it's not the case anymore with Group 2. So a few drawbacks are very important. Group 2 base oil will tend to accumulate more charges before it dissipates, and eventually you run the risk of having more violent discharge, especially around tight passages where charges accumulate a lot. Filters, bearings, but oil tank as well, because this oil is carrying this streaming current along with it, and it's not dissipating it until it gets to the reservoir. So that's where you run the chance of actually sparking inside an oil reservoir. So the question is fundamentally, can the drawbacks outweigh the benefit? And if you are faced with acute electrostatic discharge, you soon realize that the system gets overwhelmed not only with the discharges themselves, but all the degradation product that will come with the degradation of the hydrocarbon chains. So the main consequences and symptoms of an ESD problem in the system is that you will create very, very hot spots at very specific location in the system, really where charges accumulate and eventually discharge violently through the oil or through the filter material or around bearings or fine valve passages. It will burn the oil, it will attack the materials and the components, and very importantly, that's what creates sludge, varnishes, which are typical byproducts of thermal degradation of the fluid. And interestingly, you can hear that happening. The phenomenon is audible, which means that if you walk next to a large oil filter next to a turbine, if you have ESD problem, you will hear it. You will hear this banging, metallic banging going on at the filter housing location. The consequences on the fluids are tremendous. You lose your lubricating capabilities, you burn the oil. It basically negates all the oxidation resistance that you could hope for when using Group 2 base stocks. So the fluid gets overwhelmed, and where it's supposed to last longer, it actually degrades very rapidly if you have that phenomenon present. We know the consequences of varnish on components: sluggish, sticky valves, diminishing cooling ability in the heat exchanger, inability to control start and stop condition, all the way to a fail to start condition on a turbine that you're trying to turn on. So I want to spend just one slide specifically on the filter issue, really to talk about how filter technology evolved and the possible consequences on the phenomenon of electrostatic discharge. Here's what we want when we make filters. We want a filter that lasts longer, so you get more surface area packed in the same volume. You want environmental advantage, and typically filter technology has evolved where filters have shed their metallic components, right? We would like to have something that we can crush and burn when the filter is spent, and metallic components have slowly been eliminated from many filter element design of the latest generation. So when you get better protection because you have smaller pores, smaller passages, when you use non-conductive materials, non-metallic materials, when you use chemically stable fine fibers, for example, glass fibers, you end up with a system that can accumulate charges very easily and is terrible at dissipating them. So filters will accumulate charges. They will violently discharge into the oil, and that will in turn degrade the efficiency, and you basically lose the protection that you were hoping for the filter. So this ESD phenomenon is bad for the fluid, it's bad for the filter, and any protection you were hoping to get from using Group 2 base oil plus a superb filters may be negated because you basically destroy both the oil and the filter. Thankfully, we can study this phenomenon and we can hope to improve it. So accumulation of charge in a filter can be measured and can be tested. And very briefly on this next slide, you see what such a test filter apparatus would look like. It's quite easy actually to measure the charging of a filter material as oil goes through it. All you need to do is have a charge collector, which is a piece of conducting material. You basically put it on the filter material itself, and it will pick up all the charge that would otherwise accumulate on the filter and basically send them to a multimeter so we can measure the rate at which the filter material is charging. So once we can measure it, we can hope to find solution, materials, designs to alleviate this problem. So this is typically what the result of a test would look like. And on this chart, you see three different color curves. One blue, which is a filter that is not equipped with a way to dissipate charge, and you see clearly how fast charge can build up inside a filter element. You compare that with the other two curves, the blue, the red, and the black. And these are surface-treated or specifically designed filters that will eliminate charges as they appear. And you can see it's fairly consistent throughout the flow rate range, so that it means that even if you increase flow rates, you are able to dissipate charges just as fast as they would accumulate otherwise. If you let a blue filter, let's say, in the system charge up this way, you'll end up with a situation where you'll discharge violently into the system. And the picture you see on the slide is an illustration of how violent this discharge can be. And this is a picture from an oil reservoir subject to discharge. So these types of arcing and extreme temperatures can happen at the filter location as well. But good news, as you can see on the slide, technology exists to really make sure that the filter does not accumulate charges as oil goes through it. And a practical illustration is shown on this slide. You see two pictures coming from lube oil filter elements that are installed, in this case, on a typical gas turbine. On the left side, you see pictures of a couple of filters that have been in place for just 3 days. They are designed to be 12 micron absolute filters, great protection for turbine bearings, but look at the state they're in after 3 days if they have experienced static discharge. What's their micron rating at this point? Only God knows. It could be anything, because really the structure, the media, the support layers have totally been burned away. And if anything, this filter has stopped protecting the machine. It's probably has contributed to the contamination that you'll find downstream in the fluid. Contrast this to the picture on the right, where you see a filter that works the same way. It's also a 12 micron absolute filter. Minute changes in the design of the material and the way the layers are supported means that this element has become anti-static. It does not accumulate charges. And you can see from the picture that after a full month of service, this filter has retained all its capability. It looks as good as almost new, other than the color of the oil that went through it. So that is the major difference, the telltale sign that something is wrong. If you ever open a filter housing and you see the picture on the left, it's a clear sign that electrostatic discharge is happening in the system. Now, this next slide is interesting. It may look complicated, but when we talk through it, you'll see that it provides a very powerful and simple message regarding filtration. This is, again, a case of 3 different filters that where we can measure the charging through the filters. So you have 3 curves, a pink, a green, and a dark blue. Obviously, you can see right away that the pink filter, which is a quote-unquote a standard 15 micron filter, seems to be charging a lot more than the other 2. So let's compare first this pink curve to the dark blue. The dark blue is a 25 micron standard filter as well, meaning non-dissipating or non-anti-static. So obviously the transition from the 25 to a 15 micron filters, we would expect the charging to go up. The passages are tighter, the micron rating is lower, etc. And this is exactly what we see here. So the amplitudes of this voltage is much smaller on the blue curve than it is on the pink curve. Now, a dangerous reaction to this phenomenon is to say, okay, I will go coarser in order to eliminate the chance of static discharge. The problem being you start to sacrifice the first goal of a filter, which is to protect the machine efficiently. Instead, let's look at what happens when you switch to what we call the ESD filter, this green curve. This is actually a 6 micron absolute filter, which is itself a lot finer than both the others. And yet, you can see from the curve that this one does not accumulate charges. It is very difficult to use fine filtration to protect the bearings without running the risk of all the consequences of static discharge, varnish and sludges, unless you apply anti-static technology. So the point I really want to make clear here is never should you sacrifice component wear protection just to reduce static discharge, because you have at your disposal tools that would allow to go both finer in protection and at the same time prevent ESD problems. So, we are this presentation, and I want to give you a couple of important other considerations that we may not have time to cover today, but are important to keep in mind and will be the subject of further webinars in the future. Other sources of thermal degradation, other than the static discharge, will also have similar consequences. Fluid degradation, tremendously hot spots, degradation of components, etc. Microdieseling is a big part of that phenomenon, and it's related to the amount of air bubbles present in the system. The use of high temperature treatment that we sometimes apply to lube oil tanks is also to blame in the case of thermal degradation. So you want to avoid things like high heat treatment, high heat, high vacuum dehydration. You really want to keep in mind that the oil needs to be kept at decent temperature for fear of launching these oxidation processes that will rapidly degrade the fluid and its characteristics. Similarly, you want to pay attention to varnish potential. Varnish in itself will be the subject of a brand new webinar coming up, but in a nutshell, measuring static buildup in operation is impossible. You need to have a test. However, the consequences will become clear on the components themselves, and the presence of sludge, the presence of varnish, is sometimes a good indicator that some kind of thermal stress is being applied to the oil. So you want to keep an eye on your varnish potential. Some measurements exist to monitor the varnish tendency for the oil, and that's an important part of an oil analysis. If the system gets heavily contaminated with the byproduct of static discharge, then preventive measures are still useful, but they won't be enough. You're beyond that point, and you need to look at potential solutions to remove varnish, to remove sludges. And thankfully, these solutions exist, and I'm not going to discuss them today, but keep in mind that even if you're beyond the point where preventive measures are enough, there's still a way for you to get back to a more manageable situation on the machine. And finally, obviously, standard oil analysis may tell you what's in the oil, but it probably won't tell you what should be and is not there anymore. So pay attention to additive depletion. That's a very important clue as to how fast the fluid is degrading. And finally, in conclusion, what we've learned is that static buildup in oil is a very dangerous phenomenon and will degrade both the fluid and the actual machine components. New and efficient filter designs are important to protect the machines, but they're also potentially contributors to static discharge problems unless they are designed to be anti-static. These static problems will increase with new oil formulation, and we looked at the case of Group 2 base oils, and these are very prominent issues when it comes to potentially static discharge. The filter industry started to study the issue over 10 years ago. And so today, technical solutions exist so that you don't have to sacrifice filtration efficiency in order to avoid static buildup. And that's an important point to remember, because getting rid of static discharge in filters should never mean that you need to sacrifice other characteristics of filtration, because wear protection is really job number one for a good filter. So to protect the fluid, and really to get to the point where Group 2 base oils are really giving the benefits that we are expecting from them, then other types of issues should be addressed as well, other than this electrostatic discharge. And I mentioned briefly the issues of air entrainment and micro-dieseling that is associated with it, moistures and wear metal controls. All these issues play a part in how potentially the fluid will degrade thermally and through oxidation. So it's also important to keep an eye on those two things. So I'd like to thank you. It's been a pleasure for me to be with you today. I hope this session was informative, and I will now pick up a couple of questions that we've received and see if we can bring clarity to a couple of points. Okay, so we've got a couple of questions, and I'll start, in order. Timothy is asking whether, because vacuum dehydration is pretty typical treatment process on those machines, how high would a vacuum need to be to create problems? Well, Timothy, really, in vacuum itself is not really the issue here, but it becomes an issue when high vacuum is combined with high heat. So things like a flash distillation unit, which pushes vacuum very hard, but also pushes heat very hard. So we're more concerned about the heat when it comes to thermal degradation. Now, too high of a vacuum can have other effects, like basically getting rid of some of the more volatile components that you'd like to stay in the oil. But I would say in general, the problem with high heat, high vacuum when it comes to what we're talking about today. The problem comes from the heat rather than the vacuum. Okay. Carlos is asking what influence, if any, has the presence of water on static discharge. All right, so if we consider water to be pure H2O, then you would consider that that's a pretty non-conductive and therefore would participate in making the oil non-conductive and therefore increase this problem. But that's never the case, right? Because you never have H2O. You have water that contains minerals and contains all kinds of things that water has been picking up on its way into the system. So the real effect of water is actually to increase the conductivity of an oil. Systems that are wet, in the sense of where the oil is fairly contaminated with water, will tend to have lower problems with electrostatic discharge because the charge tend to be dissipating quite fast. Many other problems make it that you should remove water from a turbine lube oil. Deal with electrostatic discharge in another way, but making the oil wet is really not a solution. So overall, water per se has an influence or a decreasing influence on static discharge, but it's nowhere close to a solution. Always make sure that your water content is well below saturation in a turbine oil system. Mike is asking, how do you ground a filter if you want to eliminate discharge? And that's a very good question, and I think it goes back to really the definition of what we mean by the filter, right? So you have the metallic housing, and then you have the filter element inside. It's impossible to, or let's say if the filter element itself is non-conductive, grounding it is difficult, right? You would need to run some kind of wire directly onto the filter element. Grounding the filter housing is possible, right, from the outside, but that's not really where the problem is going to be created. So the bottom line remains the filter, when you put it in, should already have some anti-static property to work properly. Going back after the filter is in place and trying to somehow ground it will really not work and be possible. Okay. Frank asks, can additives make an oil more subject to electrostatic discharge? Well, not really. I mean, obviously, there are many different types of additives, but in general, these are compounds that would actually have a fairly high conductivity. So the issue of an oil being resistive mostly comes from the base stock itself. So that's why we talked about this group 2 issue. So it's more related to the base stock. Now, the additive package is going to be one of the first victims of the problem. Not necessarily a contributor, but you will degrade and deplete your additive package through many factors, oxidation, acidification, and obviously thermal stresses here. But as such, they are not a big contributor to the phenomenon itself. And finally, one last question I have here from Matt, who's asking, how coarse do you have to be not to charge up a filter element? It's a tough question. I should almost say I don't want to answer this question because it's never a solution, as I explained, to go coarser in order to eliminate static discharge. The scientific reason, or explanation is that there is really no limit. It all depends on fluid density, fluid velocity. So you can have a coarse filter and still create charge if the dynamics are there for it. Now, in reality, from our own experience, we've noticed that if you go above the 15 micron range, the phenomenon of ESD dramatically drops, kind of regardless of the conditions of the oil. But that's really more of a feeling and experience limit rather than a scientific one, because in theory, you could charge in many other conditions if the environment itself is non-conductive. So I would say if your machine only requires protection above 15 micron, then ESD may not be a problem. But never think that if your machine needs a 6 micron filter, you'll be better off doing a 20 micron just to eliminate ESD. I explained clearly that the drawbacks of not protecting the bearings, the servos, and the fluid itself with a good filter will dramatically outweigh any gain you may think you're getting from not creating ESD. So that was the last question I had today. So this was great. I really would like to thank all of you. Again, keep an eye for more webinars dealing with other types of issues on machines and power systems in general. It'll be my pleasure to welcome you again very soon. And on this note, everybody have a great day. It's been a pleasure, and I hope to see you all again soon. Take care. Bye-bye.